Hey, what's up guys? My name is Cherno. Welcome back to my game engine series. So today we've got something a little bit different. First of all, I want you guys to watch the previous episode if you haven't already. That's us finishing up all of the I am GUI stuff that I wanted to actually do. Now that we've done that, we're going to move on to a very big new topic called rendering. Now, first of all, let's talk about what's different in this episode. My computer has just completely broken itself, like just will not work at all. Which is all great, and I could probably fix it if I had enough time, but unfortunately I don't have time because at the moment I'm working full-time, of course, at EA on Frostbite. I'm also renovating my apartment. I'm also getting married in about a month, so I have to do a lot of wedding preparation and my life is just completely hectic, but I still really wanted to make a video for you guys today, so I thought, you know what, let's just talk about stuff today, because this whole rendering topic that we're about to dive into is so incredibly complicated and just enormous that you just really cannot plan enough. And if I think about how many times I've written a renderer before and how many times I've written rendering API abstractions before, it doesn't matter how many times I do this. I'm going to be 50 years old and I'm still going to be writing them a different way because it's just incredible. Like, it's just crazy how just complicated and how much stuff there is to actually know, and I still don't really know what I'm doing. So because my computer's broken and I can't really do anything of it, I've gone to pen and paper, and we're actually going to talk about a lot of what we're going to do in the coming weeks, because what we're going to do now in Hazel is write a renderer, basically, okay? So what does that mean? Today we're going to talk about what that means exactly. And next week, what I want to do is actually put together probably like a PowerPoint presentation with like diagrams and like the structure of the API and everything we're doing in more of a formal kind of format. This video right now is actually going live for everyone at the same time, so patrons aren't getting this video early just because of the fact that I've had no computer, and I'm probably going to have to edit this on my laptop, which is going to be terrible. Anyway, that aside, everyone's getting this at the same time, which is cool because I can get your feedback immediately, and that's going to be quite good because next week what I want to actually do is record a video where I actually talk about the design of this whole thing, right? And that's going to be like with a PowerPoint kind of presentation, because there's no way I can just talk myself into this. It's just going to be too much information, and it's going to be very hard to kind of visualize if it's not drawn like as an actual diagram for you guys. So that's what's going to happen next week. But today we're just going to talk about this. I'm just going to give you my experience with just rendering in general and talk about what this means for Hazel, and like we're just going to talk, okay? So step one, and the first thing that I have on my list here is just that it's a really hard and complex topic. We should probably define what the topic actually is. So rendering, what does rendering involve? Why do we need it in a game engine? You know, what is its purpose? Why is it in Hazel? What does it do? Okay, so rendering refers to basically our ability to draw graphics on the screen. Now, what that means usually is, well, hey, I have like this 3D model I want to draw. I have this world I want to draw. I have this whole scene that I've built up. I want to render this in a real-time fashion that is, you know, fast enough to actually be real-time. So probably 60 frames per second, which is 16.7 milliseconds per frame. And I want it to be interactive, which means that there has to be fairly low latency between input and actual, you know, it doing something and affecting the rendering in some way. That is essentially what rendering is. Now, why is it so complicated? Well, the way that we achieve rendering that is fast and that is capable of producing high fidelity graphics, which again is I can't believe I did that. See, I'm not professional at all. The way that we produce something that is high fidelity, right, which is again a term that, like, to each their own, right? Like, what is high resolution? What's high fidelity graphics to you, right? A lot of what you see today is maybe some of the like new games that are being released by huge companies. You know, you see, like, I might even play some of them here. I don't know if I can copyright wise, but you know, stuff like the new ray tracing stuff in Battlefield 5. You know, you've got all of these kind of high fidelity graphics that are coming out. And we perceive them as high fidelity usually because they're close to being photorealistic, which means that rendering technology is actually capable of somewhat producing something that looks like a movie or a photograph in real time, right? And people compare it to how the real world works a lot, and you have these things like physically based rendering, which is actually rendering based on physical properties of surfaces and like how light works and photons and all of that kind of stuff. And that's kind of our pursuit us actually pursuing a way to render photorealistic graphics in real time, because we can more or less render photorealistic graphics, right? But doing it in real time is really, really challenging, and there's like a huge thing going on with people obviously trying to achieve that in real time, but that's still kind of not really quite there yet. And certainly this kind of ray tracing hardware that's coming out in the form of like RTX, for example, on NVIDIA, that stuff is definitely like stepping into the right direction, because everyone knows that ray tracing is how a lot of offline renderers, so non-real-time renderers, so renderers that people use for like movies and stuff like that, how they're able to achieve photorealism, like quote unquote, right, is by using ray tracing kind of renderers. But anyway, getting ahead of myself here. It's very complicated, because apart from doing all of that, the way that we actually achieve that high performance, or performance that is at the level where it's possible for us to do this stuff in real time and still achieve a high fidelity look, we need to use something called the GPU, which is the graphics processing unit. It's a dedicated piece of hardware that resides in most computers, right? Sometimes it's integrated into our CPU. There are various architectures for how this hardware is actually set up, but ultimately it is a dedicated chip that is on our computer or our whatever device we're using that is capable of performing or executing certain mathematical operations or algorithms that are very common for common like rendering tasks, essentially, or common graphics processing tasks. So a lot of what we have to do with graphics is display a large number of pixels on the screen. If we have a full HD display that's about 2 million pixels, we need a way to determine the color for each pixel. Usually this is independent of every other pixel, so it's possible to do that stuff in parallel, right? That is something that a GPU is usually quite good at. Okay, other things like, we deal a lot with 4-component vectors, we deal a lot with 4x4 matrices. We have hardware optimizations for operations like that on the GPU, which is why it's faster than doing these kinds of things on the CPU. So parallel processing and then a lot of specific math operations is the gist of it. Obviously, we have specific like ray tracing processes and other kind of architectures that may have a lot of things, but that's kind of just to dumb it down and to keep it basic. It's because of that. It's because the math that we kind of want to use for rendering graphics is faster to do on the GPU because of dedicated hardware for that. And then also we have a large, like huge parallelization essentially that lets us do a lot of operations in just at the same time, essentially, like in parallel. Okay, so to interface with this GPU, we have to use something called a rendering API. Now, I do have an OpenGL series which you can check out, but I do realize as time goes on, OpenGL is becoming less and less a thing. And I mean, look, me personally, like if you ask me personally, what is Jan Chernikov, what is the Cherno going to use in his high performance engine? Is it going to be OpenGL? Of course not. OpenGL is not something that I can recommend using if you're going for bleeding edge, cutting like edge, I don't know, I want to make the best game engine, the best graphics rendering engine in 2019. Of course not. You don't want OpenGL. You probably, if you're absolutely at the top edge, you want probably the Vulkan or DirectX 12, right? We are not a huge game studio or a huge rendering powerhouse that is capable of implementing a Vulkan or a DirectX 12 renderer immediately in a way that can also teach it to all of you guys, because Vulkan and DirectX 12, specifically looking at Vulkan though, is extremely complicated. Those of you who have not taken a good look at Vulkan, there is no one to me capable of explaining exactly how like the Vulkan swap chain actually works and how like OpenGL code, right? I can write you probably a physically based renderer from memory in OpenGL, like all API commands, everything just correct, right? I can do that because it's simple. Vulkan, I probably wouldn't be able to draw a triangle for you in Vulkan off the top of my head. No way, no, I definitely wouldn't be able to, right? And I've worked with Vulkan since before it was released, actually. So I do have quite a bit of Vulkan experience, and yet I'm not able to do that because it's incredibly complicated. Like 1,500 lines of code or something to render a triangle. So that's why I've specifically gone with OpenGL as a rendering API in the beginning. Why? Is it because it's the best choice? Obviously not. But the thing is, I can't spend 100 videos setting up a Vulkan swap chain to show you guys this, because that's going to lose a lot of viewers and that's not going to be interesting, okay? And it's not something that we need. Why? Because I'd much rather get Hazel to the point where I can render like a PBR scene in 3D and then be like, hey, you know what, maybe now we'll implement Vulkan because we're getting to the point where it might be necessary. So you have to look at it from this kind of point of view. A lot of people ask me if the way that I'm building Hazel is how I would build my engine or if I'm making all the right decisions. I'm making the right decisions considering it's a video series on YouTube. I want to make that absolutely clear. I actually quite like this video. I'm just ranting a lot. I'm venting. I'm just explaining how everything's working, which is good because there's so many comments I've read and so many things I wanted to say, but I can't. Anyway. So, that being said, that's why we've kind of chosen OpenGL, because it allows us to tap into our graphics card and actually use it, but it's the most simple API for doing that. OpenGL is extremely simple. It's like a 10 out of 10 in terms of how high level of an abstraction it is, right? Whereas Vulkan might be like a 1, DirectX 12 might be like a 3, DirectX 11 and like Metal might be around a 5 or 6. Whereas Vulkan is like, you know, on one extreme and OpenGL is on the other extreme, which is quite interesting as well to just look at. Okay, so here's where it gets even more complicated though. So, okay, you pick a rendering API, which lets you use the graphics card, which is what you want to do to perform rendering, right? That's our task in a way. But the problem is one graphics API is not enough. Now, OpenGL is something that happens to, at least in the past, now more so it's getting more deprecated and it's getting more or less kind of removed, like channeled out, whatever you want to call it. So it's a little bit different now. But in the past, OpenGL was extremely good in the sense that it just worked on everything. It was almost like Java. Actually, I might compare it to Java because Java worked asterisk everywhere, but it was mostly garbage, right? I wouldn't say OpenGL is like just absolute garbage or anything like that. I actually quite like OpenGL in the sense that it's just so simple. It's so nice and warm and inviting to come back to OpenGL after spending some time in other rendering APIs and being like, this is insane. It's nice to come back to OpenGL in a way, even though I still think the API is not amazing. It's still nice to come back to OpenGL, and not amazing, I'm putting it lightly, by the way. But anyway, coming back to OpenGL is always nice because it's so simple, right? It's incredibly simple. Now, the thing is though, and I don't even remember where I was going with this, but the thing is, when you have something really, when you go back to designing all of these rendering APIs and you think about what you actually need, it becomes a problem of what platforms essentially am I kind of shipping on, right? So to drag this back a little bit, as I was just talking earlier before I completely forgot where I was going, I was saying that OpenGL back in the day was kind of just like Java in the sense that it just worked everywhere, right? I mean, Windows, Mac, Linux, Android, iOS, they were all capable of running OpenGL. Whereas now if you take a look at what's happening, well, like, you know, not saying Windows wasn't absolutely great with it, but like Android, iOS, you know, Mac, Linux, they all kind of ran on it, right? But now if you look at the state of APIs, what is the best API to render on a given platform? For Windows, it's DirectX 11 or DirectX 12. For Mac, it's Metal. And for iOS, it's Metal. For Linux, it's Vulkan. For Android, it's Vulkan. Maybe GLES, right? GLES, but that's for probably older devices, mostly Vulkan, right? Did I miss anything? For Xbox, it's DirectX 12, usually. And for PS4, which I'm missing out on, is Sony's own proprietary API, which I always forget the name of because I don't deal with it too often. And then for like the Nintendo Switch, I think it might be Vulkan as well, to be honest, but I'm not 100% sure. Anyway, for those kind of platforms, you can see that OpenGL is non-existent, right? Do I pick OpenGL? Well, no. Maybe on older Android devices is pretty much maybe the only reason you pick OpenGL, right? You can still render OpenGL on Windows, but is it preferred? No. You should be using DirectX if you're serious about rendering on Windows. It's as simple as that. Where I'm going with this is that you need to you can't get away with using one rendering API, and that's why rendering becomes really complicated. Well, one of the reasons it becomes complicated, because you need to do something, you need to design an API abstraction which hides away all of the actual render API like calls behind your own abstraction, so that ideally you basically, or in this case Hazel, has its own API. It has its own rendering API And then that rendering API could be using either DirectX 12, could be using DirectX 11, could be using Vulkan, could be using GL, could be using Metal, whatever, right? It could be using any rendering API it wants, but you tell Hazel, I want to upload a vertex buffer full of data, it does that. How it does that, using which API, that's implementation details that we don't want to worry about. We have this abstraction layer, an API where we can generically tell Hazel, upload this vertex buffer, upload this texture data, I want to render, from this index buffer 3 indices, and with this vertex buffer, with this material, with this shader, with this, topology, I don't know, just a million different details, right? But the point is, we tell Hazel we want that. Hazel figures out, okay, well, we're running on Windows and we're currently using DirectX 11 because that's what we've selected, therefore I'm going to use that. Or we're currently running on a Mac, so I'm going to use Metal, you kind of get the point, right? We have this abstraction layer so that our application code doesn't change based on what it's running on, and it will be using the optimal rendering API on the platform and configuration that we've actually set up. That's extremely difficult to do, okay? That's extremely difficult to do, because what you need to do is draw a line somewhere and say, this is what my API looks like. That's really difficult, because the more you go on with graphics and the further you get and the more advanced techniques you start implementing, you may need more control. Dragging the whole API line is a huge and expensive task to do. In case you guys aren't clear about what I mean by API line, it's where you draw the abstraction. So in other words, where really high level might be draw a triangle at this location, and really low level might be like unlock my Vulkan semaphore, right? That's kind of maybe the two extremes, or like, release this memory fence or whatever. Like where you draw the line is really important, right? Now, usually what I tend to do is I like to think of it conceptually. So things like, did I just do that again? Twice in one video, man. Anyway, so we kind of draw the line at a point where, like, I might want to say, I want a vertex buffer, I want an index buffer, I want a texture, I want a shader, I want to, what API exists on the shader? Well, I want to find out information about my uniforms, my attributes. I want to be able to set up uniform buffers. I want to be able to kind of upload sections of uniform buffers. I might want to retrieve information about attributes. I might want to retrieve certain other information, right? There's a lot of things that you might want to do. I might want to get all the resources attached to that shader, such as different textures and like samplers, maybe like how many textures, how many outputs does this shader have? Do I have to hook them up to frame buffers? You have to kind of have an API that is flexible enough that allows you to implement all these rendering techniques, but also abstracts away all of these APIs. But here's the other problem. These APIs do not work the same way, right? These APIs do not work the same way. OpenGL is completely different to Vulkan, right? I mean, yes, conceptually, you can abstract it out and say, okay, how do I render a triangle? Conceptually, what you could say is, okay, well, what do I need for that? I need to, first of all, set up some kind of context, right? In Vulkan, you'd have to set up like a crazy amount of things, such as like command queues, rendering devices, like logical devices, physical devices. What else is there? Queues, instances. I don't even remember everything I can't even list all the things you need to set up in Vulkan. There's a lot of stuff you need to set up, whereas in OpenGL might just be like, okay, fine, and frame buffers obviously in Vulkan as well. Like you need to get all the swap chain. You need to set up your swap chain and set up frame buffers for each buffer in the swap chain. Lots of stuff you need to do, but essentially it comes down to, I set up my context and my rendering frame buffer, right? I upload a vertex buffer with vertices. I upload an index buffer with indices. I upload a shader. I set my viewport maybe and other kind of rendering context things, and then I issue a draw call. That's probably about it, right? That's what I do. And like obviously that process in Vulkan is going to require a lot more code, but that might be that might be the steps that you need to actually render a triangle on the screen. So with that in mind, you kind of have enough to go on where you can say, I can make this work in both Vulkan and OpenGL because I know what I need, I know my steps, and they're just going to look different. But essentially, I've drawn that line at, I have a vertex buffer class, that's where my abstraction ends, right? So inside that vertex buffer class, I'll have a different implementation of that vertex buffer class, which applies to Vulkan and GL, for example, right? And then the API that will be exposed are things like, I want to create a vertex buffer, it should be this many bytes, right? It should be this kind of usage, so like whether it's kind of dynamic or static, things like that. I want to be able to upload a section. I want to be able to maybe map the buffer or upload a section of data to a particular offset in the buffer. So I want that API available. I want to be able to see the size of the buffer. I want to be able to set the layout of the buffer so that we know how to actually render with it and what the data inside there looks like. Those kinds of things, right? I want to bind the buffer. I want to, lots of stuff to do, right? But the idea is you've created an API. So that's really the first thing that we need to kind of do. We need to create a rendering API. Now, there is no way I'm going to sit down here and write you every single class and every single detail right now, because that'll be extremely lengthy. And that's like designing a whole specification. We're going to do it as we go along. But as I said, next time when I have like a little PowerPoint presentation for you guys, that's where, and I'm going to take in probably some suggestions from the comments as well, from people who are experienced in this, just because like, I've been doing this for years and years and years and years, and professionally as well, obviously. And I'm more than open to ideas, because this kind of stuff, sometimes I'll learn something new suddenly and I'll be like, whoa, I want to revisit this whole thing and rewrite it from scratch now that I have this piece of information, right? But anyway, so we designed an API. We need to come up with an API essentially where we draw the line of abstraction so that we actually know how kind of low level that'll be. Usually what ends up happening, by the way, is that you have like kind of a, you have your render API abstraction layer, and then on top of that you have a renderer. So you don't, like, the renderer does not directly interface with any rendering API, but you still kind of have that, right? So the renderer layer is where you probably have things like your scene graph, any kind of batching logic, culling logic, that kind of stuff. That's at like that renderer level, right? And like render sorting and all of that kind of stuff, right? Whereas, the render API doesn't deal with it. The render API is things like upload a vertex buffer, upload a texture. It's like render commands, essentially, but you've abstracted it out so that you can switch out the rendering API to whatever you want, okay? So that's the API that we need to design. We're not going to talk about the renderer just yet. We're just going to talk about that rendering API abstraction. That's one thing we need to do, and we'll talk about that next week. I've got a lot of other things here as well. There are things like command queues and multi-threading, and I don't mean renderer multi-threading, I mean like game engine multi-threading. So it's very common, for example, to actually submit commands from your game thread or from your application thread, but all that is a command submission. So you say, I want to upload this texture, or please create a vertex buffer for me on the GPU, right? What happens with that code is it gets queued. It gets put into something called a command queue, or like a render command queue. And then what happens is the render thread, when that starts up, it goes through the list of commands and executes them, okay? A lot of APIs actually do stuff like this, like Vulkan and DirectX 12, for example, have that stuff in them, but like GL doesn't. So usually it's common nowadays to actually design that stuff yourself. We'll have to do that, right? Probably. And I'll show you guys how to do that, because it's quite, it's quite cool. I quite like it, even though it is sometimes tedious. But essentially you have like a command encoder that goes through and like it copies all the data you need for a command, plus the command itself, plus maybe like a function pointer. And then you store all of that in like a binary buffer that's all contiguous memory, so that it's all kind of cache friendly. And then the render thread goes through that, and like it's almost like a CPU reading CPU instructions, where you go through like different opcodes and you say, okay, I'm doing this command now. The next 12 bytes are parameters in the form of 3 floats. So transmit them like that. And it's actually quite interesting. And you can make it very efficient, which is really cool. So we'll have to cover stuff like that. And we'll talk about some of the negatives of that as well as the positives. There's a lot to do with rendering. I just want you guys to understand that. I'm kind of overwhelmed. I want to design this as much as possible. I always knew this would happen in a way, but like, it's almost annoying that we're up to rendering now, because as I said, I'm getting married next month, and then I'm going to go on a honeymoon for a little bit of time, so I'll be away and there won't be videos here, and obviously I don't want to be worrying about rendering architecture in Hazel while I'm supposed to be getting married. So because of that, I'm just like asking you guys to just take it easy on me for the next month or two, probably 2 months. Like in May, I should be back in action 100%. But like for now, I'm gonna still try and release a video a week. But if it's like not as saturated or not as good as you kind of, not as much, we don't get as much done as you expect to, it's because I just kind of want to talk this through. I want to make sure we have a solid design, because this is probably one of the most complicated parts of Hazel. It's definitely the biggest system of Hazel. And I definitely want to just make sure that we get this kind of right, but also that you guys understand all the implications with this, because this is an educational series. I'm not just writing Hazel for myself. We're building Hazel together, and I want you guys to understand how everything works. Anyway, I think that's about it. Next time, what we're actually going to do is talk about that rendering API abstraction. I'm going to see what you guys say in the comments, but also I'm going to get that PowerPoint presentation ready where we actually talk about how we are going to abstract that and what it's going to turn into, and how everything's going to work. The whole architecture of the renderer is really what we're going to talk about next week, and not really the architecture of the renderer so much as the architecture of the render API abstraction, or the rendering API, graphics API abstraction, whatever you want to call it. Okay, so that's next week. Hope you guys enjoyed this video, and I need to fix my computer before next week as well, so this is not going to be a fun week anyway. And we've got people from like Frostbite over in the EA studio this week as well. There's so much stuff happening. I hope you guys enjoyed this video. If you did, please hit that like button. You can help support me on Patreon by going to patreon.com/thecherno. I need you guys' support more than ever right now, because I'm just like, I'm thinking of even taking like unpaid leave from work, because it's just, everything is just overwhelming. So I would, I really want to keep making these videos for you guys. Because I love it, right? Like, even though there are potentially more important things for me to be doing right now, I really love making these videos for you guys. Like, you mean a lot to me, and I really do want to write this renderer for Hazel. It's going to be so cool, and working with you guys as well on that is going to be amazing. So if you can, please support me, and you'll get access to a lot of this source code. I've already written like a render command queue, that runs like on a different thread. I don't think it runs on a different thread yet, but it is a full kind of command processor and command queue, where you can submit commands. I've already written all that stuff, and it works with OpenGL, and we are rendering more than just a triangle. All that stuff is in the Hazel development repository, already ready to go. So if you want to kind of jump ahead and see kind of how this is going to look, definitely check that out. And I think that I am, because that is OpenGL, I'm not sure exactly where, but I am already beginning that abstraction. So I'm playing around with things like that. So definitely check that out. And then usually you'll get videos a week early. I can't promise for the next like 2 months, basically until May, that you will get videos early every week. I'll try, but with this week, I kind of couldn't do that because of my computer. Maybe that'll be better. But again, your support means a lot to me. And this series, I'm telling you, like, straight up, would not be here without all of those wonderful supporters. So thank you so much. Hope you guys enjoyed this video. I will see you next time. Goodbye.